Today, the topic of my talk is actually the lower dimensional topological information. We're going to touch a little bit of theory and also a little bit of applications. So my background is statistician. So compared to previous talk, today's talk will involve a little bit more data analysis and also statistical elements. I hope you enjoy it. So today's talk will be separated into two portions. In the first part, we're going to focus more on the theory development. To be more precise, we're going to focus in the lower dimensional topological feature, a specific lower dimensional topological feature, what we call the lower dimensional zero density region. And in the second part, we're going to try to incorporate the one kind of lower dimensional topological feature into a very specific application problem, which is the image segmentation problem. And then I'll wrap up my talk with a little bit summary of future works. Now let's start with the theory part. If you look at this nice figure, the orange surface is actually representing a surface of a probability density function, while those two red intersecting circles are the regions over which the probability density function evaluates at 0. So the two intersecting red circles are actually showing non-trivial topological features. So one of our grand goal is that, well, by looking at the non-trivial topological feature, we hope such a feature will reflect the probability properties of the density function itself. So to start with, I'll briefly introduce the topological data analysis, which is data analytic techniques that construct a sequence of topological space known as the complexes to approximate the underlying topology of the space where the data set lives in. And from a perspective of a statistician, a more interesting or a more specific problem we concern is to study the topology of the probability density function, or the topology of the support of the probability density function. We suppose that when the IID sample points were drawn from such a density function, and then hopefully the data set itself will reflect the topology of the support of the probability density function. In the following work, we're giving a set of sufficient conditions under which the lower dimensional topological features can be asymptotically detected directly. And this description will be more clear as we move along this talk. So before I introduce our object of interest, I want to briefly review the current research into this direction, the topology of the support of the probability density function, or more generally, the topology of the probability density function. So topologists will often ask for strictly positive full support in order to recover the topology of the support of probability density function. For example, the foundational work by Minkowski, Smell, and Weinberger, they actually says that with sufficient samples drawn from the density function, you can actually recover the underlying manifold with a high probability. From the perspective of statisticians, we are focusing on a more regular object, which is the level set of a probability density function, defined as the inverse image of an open interval, like this. So for such object, statisticians develop various kinds of level set estimators, and they were basically categorized into two major approaches. One is known as the plug-in estimator, while the other is known as the excessive mass. So under some regularity assumptions, both kinds of estimator have acute consistency properties as well as the asymptotic properties, for example, central limit theorem. Our object of interest is even more specific. So we're defining the lower dimensional zero density region to be a zero level set, which means that it's an inverse image of a single point set as 0. we're sort of abusing the terminology here because, well, now we're investigating the inverse image of a single set which contains only zero point 0 instead of an interval like defined above. And then we derive a covering scheme in order to detect such a zero density region. So the S0 actually serves as the boundary of the manifold of the zero level set F inverse 0 to infinity. And our methods can actually be generalized to a more general scenario. However, for simplicity, we're focusing on this S0, which is the inverse image of a one-point set. So the zero density region, a strictly lower dimensional zero density region, consists of several adjectives. We already explained why it is called zero density region. Then next, we're going to describe what do we actually mean by lower dimensional. There are various kinds of dimensionality in the mathematics world. In this specific work, we're focusing on the Minkowski dimension, which is basically a description of the topological complexity of a certain set. So for a covering consisting of an open covering ball of radius delta, we can define a minimal covering number intuitively. It means that the minimal number of covering balls we needed to actually cover such a set E. Notice that now we're using open covering balls. If you're using closed covering balls, the definition will be slightly different. And then, after we define the minimal covering number or delta minimal covering number or delta covering number, we take the log ratio of the covering number and the radius and study their upper and lower limits. And these are actually defined as the Minkowski upper and lower Minkowski dimension. So as we all know, well, these two kinds of limits do not even have to exist. And even if they exist, they do not have to go inside. For a very simple example, if your underlying set E is actually a fractal, the fractal shows different the fractal actually has different minimal covering number at different scales. So it's very likely that your upper and lower Minkowski dimension will be different for a fractal set. And then next, since we're studying the support of a probability density function, we also need the definition of what we mean by support. This is pretty classical. It's just an intersection of all the closed set over which the probability density function got a probability mass 1. However, again, to simplify the question a little bit, we actually assume the support to be d-dimensional unit hypercube in our following discussion. This d-dimensional unit hypercube will obviously have the Minkowski dimension d. Actually, for smooth manifolds, the manifold dimension will coincide with its Minkowski dimension. So, however, our main result can be generalized to smooth manifold M with more complicated notation, of course. And now we are ready to give a rigorous definition of what the object we're interested in. So the object we're interested in is called a strictly lower dimensional zero density region. First of all, we study the inverse image of a one-point set 0 and denoted by S0. And then we stipulated that this S0 has a strictly lower Minkowski dimension compared to the d-dimensional unit hypercube. So let's look at an illustrative example. In this figure, the orange surface is still denoting the density function. Both density functions share the same zero density region, which is the red line segment in the middle of the two-dimensional unit hypercube. The line segment obviously has Minkowski dimension 1, while the support of the both density function have Minkowski dimension 2. The difference is that on the left-hand side, the probability density function is actually proportional to the square of the point to set distance, while on the right-hand side, the probability density function is actually proportional to the fourth power of the point to set distance. So as we observe here, these two density functions have very different local behavior near the zero density region. So now the second question, a very interesting one, arises that actually how to characterize this different behavior of density functions near the same zero density region as zero. So in order to describe such different local behaviors, we are going to introduce a new notion in our paper, which we call the order of smoothness. So first of all, we restrict our attention to an epsilon neighborhood of the zero density region, and then we compare the density function to a polynomial order of the point to set distance. And by taking inf and sup again, we define them to be the upper and lower order of smoothness. And then we take the limit as the parameter epsilon, or the neighborhood of the zero density region, shrink it to 0, and then take these two limits to be the upper and lower order of smoothness with respect to this specific zero density region as 0. Again, these limits do not have to exist, and even if they exist, they do not have to coincide. So in order to make this a little bit more clear, let's look back to the same example. On the left-hand side, the upper and lower order of smoothness are both 2 because they are proportional to the square of the point to set distance. And on the right-hand side, both upper and lower order of smoothness will be 4. However, if on this area is to the fourth power, on this area is to the square, then the upper will be 2 and the lower, the lower will be 2 and the upper will be 4. And from another perspective, this notion of order of smoothness is a generalization of the Holder continuity. However, it's more general than that because some density function without Holder continuity, we could still calculate its order of smoothness. To give you a more specific example will be, well, if your density function is analytic, then you can do the Taylor expansion. Then the order of smoothness is always integer in that case, and you can read it from the first non-vanishing term. So now, after we introduce so many notions, we're going to describe briefly our detection method. It was a scale covering scheme, and it could be described in 3 major steps. First, we use a sequence of family of covering balls to covering the whole support, which is the d-dimensional unit hypercube. And then we scale this covering balls. That is, as the sample size tends to infinity, we shrink the radius of the covering ball. And also we shrink the parameter epsilon that create an epsilon neighborhood of the zero density region. And the final step is that we classify different kinds of covering balls and observe their behavior in order to detect as 0. You may still wonder, oh yeah, it's still kind of blur. However, maybe we should look at a simulation example. In this example, we still studying the line segment example with the probability density function proportional to the fourth power of the point to set distance. And then we draw a sample of size 100 to 100,000. In these figures, the red dots are those sample points drawn from this density function. And those transparent black balls are those covering balls that contain at least one red dot, means one sample, so they are non-empty. While the white areas were covered by empty covering balls, which are the covering balls contains no red dots or no sample points at all. So as you can see from left to right, as the sample size grows to infinity, we shrink the radius of the covering ball, and the empty covering ball align at the location of the line segment. So from left to right, it's gradually clear that the white area will like merge into a not as a, well will evolve into like a white line segment area. So intuitively, you can look at those white areas that were covered by the empty covering balls in order to locate your red line segment, which is your zero density region. So to formalize this intuition a little bit, let's
And Hengrui, a question.
Sure.
Yeah, so the difficulty in your problem is you're sort of trying to recover the zero density region where none of the point samples are going to be. Is that right?
Right. So, well, I have to make an additional remark. So imagine that your support of density function is a two-dimensional cloth, and you actually got two-dimensional hole in the middle of it, and you keep drawing samples from it. By law of large number, you will eventually saw a hole in the middle of it.
Right.
However, if your hole is gone and it's just a cut, which is a one-dimensional thing, then law of large number actually fails because your lower dimensionality of your zero density region contains no probability mass at all. So that
You
makes
won't
it
measure
very
the
hard.
fact that your cloth has been cut by a knife.
Exactly. However, our method is definitely more useful than detecting a cut in your cloth. So
Cool.
so
Yeah.
like okay, that's up your question, right?
Yeah, thank you. That's very
Yeah.
nice.
So in order to formalize our method a little bit, we also need to like introduce what do we mean by different kinds of covering ball. So again, we use the line segment example. Here, the red line segment is still the zero density region. For those balls which intersecting this zero density region, we call it epsilon inside ball, like this red ones in the middle of the picture. However, for those balls whose centers were outside of the epsilon neighborhood of the zero density region, like those two green ones, but completely away from the even from the epsilon neighborhood of the zero density region, we call them like epsilon outside ball, and the rest of them we call it epsilon neighboring ball. And then intuitively, since those epsilon inside balls are so close to the zero density region, we suspect, okay, they might contain, well, relatively little probability mass. So if we shrink them appropriately, we can avoid all those sample points that would draw from this density function. And on the other hand, for those epsilon outside ball, since they're so far away from the zero density region, then we suspect, okay, they must contain relatively a lot of probability mass. And then if we don't shrink them too fast, then, well, at least one sample point will fall in each of these covering balls. And this is our basic intuition that guide us through our detection methods. And then you may ask, okay, this simulation result seems good, but the method seems quite arbitrary. And we also failed that, and therefore we come up with a theoretical guarantee that makes sure our method works. And this is our main theorem. So there are a set of regularity assumptions, of course, but let's look at the statement of the main theorem first. So our main theorem basically is prescribe the polynomial growth rate of the radius of the covering ball and also the shrinkage rate of the epsilon parameter. That allows us to detect the zero density region. For part A and part B, if both sufficient conditions are satisfied, then the limiting probability that there were no empty epsilon outside ball, as well as the limiting probability that all the epsilon inside balls are empty, will both tend to 1. So this is basically a consistency result for our covering scheme method, basically saying that it suffices that you only look at the empty covering balls, and then you will be able to figure out where the zero density region are. So before I go into the proof strategy, we should somehow still be familiar with this formidable regularity conditions. There are 6 of them. However, they could be grouped into 3 groups. The first group are basically topological restrictions of the support as well as the zero density region. For example, you cannot have like countably many connected components of zero density region. That will create trouble when you're actually going to study the limiting set of this sequence of connected components. The second group is A3 and A4. These are mild restriction on the probability density function. For example, you cannot let your probability density function oscillate too fiercely near your zero density region. That will also first, it will make the order of smoothness not calculable. And then second, it will break down the whole covering scheme. The last group of assumption, A5 and A6, are basically describing how we should design our covering scheme. So in that case, for example, you cannot actually keep stacking covering ball at the same location. That will waste a lot of the covering balls, and that also will fail our methods. So this is the technical assumptions of our main results, which guard us against the successful detection, not guard us, ensures the successful detection of the lower dimensional zero density region. So the idea of proof is also consisting of 3 steps. First is a topological steps, make sure that we can actually construct such a covering scheme that satisfies A5 and A6. It's not that complicated, but the proof is quite long. It's basically involving that clever use of minimal covering over the zero density region. That is a quite concise summary. And the second step is the probability bound for local probability. We use the concentration inequality to derive local bounds for each individual balls of different kinds. And then we just use the union bound to combine these local bounds into one probability bound. And the first step is the analysis order of magnitude, which is basically a routine that allows us to come up with the sufficient condition, which is involving the big O notation. So there are some generalization of our result. For example, the regularity condition A2 can be dropped. For example, your lower dimensional zero density region can have for example 2 components or finitely many components. One of them is a line segment while the other of them is a point. That means one of your connected component has Minkowski dimension 1 while the other connected component actually have Minkowski dimension 0. So we can also handle that kind of condition, probability density function. And then we can also generalize our result to non-compact support instead of a d-dimensional unit hypercube. The interesting thing is that there are actually 2 different approaches to generalize into this direction. One is a pretty classical probability technique, which is that we only consider 1 minus delta support, which contains 1 minus delta probability mass of all the probability density function. And then we shrink the delta to 0 as the sample size tends to infinity. And then a second approach is a little bit more complicated. It basically requires you to construct a regular transformation which transform the majority of the support back to a compact set. And that allows you to reduce the non-compact support to a compact case. So to briefly sum up and conclude our first part, the contribution in this work asymptotics of lower dimensional zero density regions, we derive a detection method which is based on a scale covering scheme that allows us to detect such a specific object, which we call the lower dimensional zero density regions lying in the support of the probability density function. And in addition, we also come up with sufficient condition for our covering method to actually works as the sample size tends to infinity. And a future work in this direction will be, instead of IID samples drawn from the probability density function, what if the samples are actually dependent, for example, from Markov chain? We already got some pretty interesting result in that direction. And then a second future work will be the mathematician will say, okay, good, we got sufficient condition, and the next natural step will be, okay, how about necessary condition for our method to work? That is also one direction that is definitely worth considering. So before I start the second part, are there any questions considering this part? Okay, then we are going to move on the application part. In this part, we are going to consider a very specific problem, which is the image segmentation problem. In this two-dimensional grayscale image, there are two skin lesions in the middle of the image. And then, well, since they are black, it is relatively easy to delineate. But overall, the ultimate goal of an image segmentation task is actually to come up with the boundary of such an object. So since the object, like the skin lesion in a two-dimensional image, is actually dimension 2, and its boundary naturally occurs as a topological feature of dimension 1. So that is also a lower dimensional topological feature, which is of specific interest in this image segmentation problem. So in this work, we are going to incorporate this kind of lower dimensional information in the boundary indirectly into a Bayesian modeling to improve the estimation of the boundary. So before we move to our proposed method, we have to introduce two existing image segmentation models. The first one is called a topological persistent segmentation, which is abbreviated as TOP. It is an unsupervised pixel clustering method consisting of basically 3 steps. First, it extracts the model set of the estimated pixel density of grayscale values of the image, because the grayscale value two-dimensional image consisting of batch of points, x coordinate, y coordinate, and the grayscale value between 0 and 1. And then after you conduct your density estimation, you use the mean shift algorithm to extract the model set and compute the topological boundary persistence between different model sets. By using these persistent parameters, you can come up with hierarchical structures, and then you cluster your pixels using these hierarchical structures. The final segmentation result will be taken as the boundary of the clusters. So in this method, since it's a clustering-based method, it's unsupervised, and then its main procedure is used for clustering the pixels, and the boundary only, the final segmentation boundary comes up as a boundary of the clusters. So it could contain actually multiple components, and also you will expect that the final boundary will be quite wiggly because it's actually basically take the boundary of the pixels. So next, we're going to introduce another image segmentation model, which is a variant of the popular active contour model, which we call the Bayesian active contour. So quite different from the TOP method, the Bayesian active contour method is actually treating the image segmentation problem as a curve estimation method, and it's also supervised. So the simple idea of this BAC method is that, well, it's basically estimating the boundary by minimizing an energy functional that relate to the boundary as well as the picture. So let's look at this so-called energy functional. it consists of like 3 weights, which are user specified, lambda 1 through lambda 3, and also 3 terms corresponding to these weights. The first term, E image, is basically like comparing the interior and exterior estimate density functions. The interior and exterior were defined by the estimated curve U. And the second term, E smooth, is an energy term that basically integral along the boundary of the curve that will take care of the smoothness of the estimated curve U. And the third term, and it's also the reason why this model is called a Bayesian active contour, is a prior term, which means that if you are going to segment a skin lesion image and you already got probably 20 image with ground truth, then you can incorporate those information into this term. You can compute the culture mean and variance of this 20 ground truth, which are 20 curves, and then put it into this prior term in a density-like form. So all in all, after you finish designing such an energy functional, you have to minimize it, and the minimizer is actually a curve. And this curve will be regarded as your final segmentation result. And this minimization is done through a gradient descent algorithm. Okay, we already introduced 2 very different image segmentation models. One is unsupervised, the other is supervised. One is clustering based, the other is actually a curve estimation philosophy. So we ask ourselves, can we actually take advantage of both perspectives? Like the first one is we are actually using topological information to do the segmentation, while the second one, we're actively treating the segmentation task as a curve estimation, and we regulated some of its geometric property, for example, smoothness, and combine this topological and shape analysis methods. Unfortunately, our answer is yes. Before that, let's look at some problem with both methods. So for the TOP method, it is so sensitive to the background noise, and it requires a lot of tuning. For example, if you actually got some white noise at the background, the top method will actually delineate all of them, and that will produce some like noise points or noise boundaries that you don't want. And then, since the final segmentation result is taken as the boundary of the cluster, it's very wiggly, and there's no way to adjust the smoothness of the result. And let's look at the BAC method. The BAC method is based on the minimization of the energy functional, and the minimization is done by a gradient descent algorithm. So we know that the gradient descent algorithm is unstable with respect to the choice of the initial points. In fact, in this specific model, the choice of initial point could be could affect the convergence speed as well as the final segmentation results quite a bit. Usually, if you don't choose your initial points appropriately, for example, as the original paper suggests, we choose a large circle in the middle of the image, it could take hundreds of steps to get the final converged result. It would take quite a long time, I promise. So we propose that, how about this? We use the segmentation result given by the TOP method and use that as an initial point of the BAC method. Then the BAC method could smooth out the segmentation result obtained from the TOP method. And since the TOP method already provide a pretty good initial point, and the BAC method will actually benefit from such a good initial point. So it turns out that this idea works and works pretty well. So next we're going to see some simulation study as well as some application on real data. So in this figure, we actually used one bone example from the MPEG-7 dataset, which is topologically trivial because it only had like one kinetic component, very straightforward and simple to segment it. Actually, a lot of classical methods performs pretty well. On the left-hand side, here we use the original image with clear binary boundary contrast, and then in the middle, we add some binary perturbations to this boundary to create some artificial noise. And on the right-hand side, we add some non-binary noise, which is a Gaussian blur, to like blur out this boundary to make some artificial noise. And then we compare the performance of all three methods we mentioned, the TOP, the BAC, and our combined method. So we use different kinds of performance evaluation measures, including Hausdorff distance between the segmentation result and the ground truth, Hamming distance, also between the segmentation result and the ground truth, and Jaccard distance, discovery rate, and the elastic shape distance. So as we see here, our combined method, TAC, is not always performs the best. However, if you look carefully at the values of performance measure, it's not far away from the optimal method. So this set of simulation study shows that in a topological trivial case, even our combined method does not perform the best all the time. It's not too far away from the optimal method. And then next, we're going to show a scenario where our combined method actually outperforms the other methods, which is a topological non-trivial case. So similar type of image, however, the object is replaced by a donut or a bagel, depending on where you come from. So here we got a donut to segment it. The donut is topological non-trivial, and then it has interior and exterior boundary. We also do the Gaussian perturbation, which is a binary perturbation in the middle of it, and a Gaussian blur at the right panel. In both cases, actually in this case, the BAC cannot identify multiple curves simultaneously because its energy functional is defined to be a functional of a single curve. If you actually just put the image into the BAC algorithm, it will create a lot of self-loops at the exterior or interior boundary, and it will create a lot of other kinds of pathological behavior when it tries to cross from the exterior boundary into the interior boundary. So in this case, we only compare the TOP method and our combined method. So as you can see that in the Gaussian perturbation case, our combined method is actually outperforms the TOP method by a large margin. And in other two cases, no noise and Gaussian blur noise, our combined method also performs pretty well. And even if it doesn't, well, it's pretty close to the TOP method. So a real data set application, again, we're focusing on the skin lesion images. So in this case, it's important to actually identify whether a specific image contains like multiple kinetic component or one large kinetic component, since that helps the doctor to determine at which stage the patient is, and also help the doctor to determine which is the optimal treatment methods. So here, we actually run through our combined methods, and it identify 3 kinetic components in the skin lesions pretty well with a reasonable smooth contour. While the TOP method will sometimes like identify also the rulers and all other noise points. And if you run through the BAC, it will only give you a large kinetic component. So Here is the real data application showing why the combined method is desirable. But all in all, in this work, combining geometry and topological information in segmentation, our contribution is actually to utilize the multi-scale information carried by topological features that can be combined with the Bayesian model's BAC in this specific image segmentation problem. However, another important motivation of this paper is that we are trying to compare the topological-based methods and a classical statistical shape analysis method, providing both qualitative and quantitative performance comparison in a very well-defined problem. And such a comparison will allow us to see these two different categories of methods, how they perform, and under what circumstances they perform better than the other one. So in the future, I will still keep looking at the multi-scale information in higher dimension and its application and design of modeling. And also an ongoing work is we're focusing on dimension reduction using the topological method with a sparsity control, which I co-author with one of our audience today, Michael, and then and then we got pretty interesting result in that. So to wrap up today's talk, I will wrap up by asking myself the big question: how can topological information be used effectively in statistical and data analysis? And since the TDA, there are three letters, and DA means data analysis, so well, the data analysis must be a very important component of the TDA community. And in the first half, I discussed a work that we're focusing on the lower dimensional zero density region. And we come up with a covering scheme, and its consistency guarantees allows us to detect such a kind of specific lower dimensional features. And in the second half of the talk, we investigated another specific topological feature, which arises as the boundary of the manifold. And then we showed that by using such a topological information, we can actually improve a fairly classical Bayesian active contour model. So I'll wrap up my talk by saying that topology is useful in our everyday life, even if you are actually putting your mug and eating a donut. So I'll end up here, and thank you all again for the attention, and questions are very welcome. Thank you.
Thank you. So questions. So don't forget to ask a question. So right now everybody is set to mute. So if you want to ask a question, you have to unmute yourself first.
I think I have a question concerning sensitivity and specificity. So the performance comparisons you showed basically address the specificity of those methods, right?
Right, right.
How about the sensitivity between those?
That's a very good question we haven't included in our current work. So in our appendix of the current archive drafts, we only provide performance measures like what we've seen today. However, it's definitely a useful, it's definitely a very helpful thing to know the sensitivity analysis results for our method and other methods that we haven't done yet. But yeah, it's a good question that we certainly wish we could do in the future.
Yeah, I think that's one very important thing to know about if you want to actually apply it to like real world data.
Yeah, that's absolutely true. So as I also said, that one of the motivation, actually our first motivation of this paper is to compare like a topological based and geometrical based method, and then the combined method is actually like built upon this comparison. So, but overall, I think the sensitivity analysis is very important, and that needs to be done. Yep.
Okay, other questions?
I had a question. So, Hengrui, in the first part of your talk, are you recovering the connected components of the density zero region, or are you also trying to recover the shape of the connected components of the density zero regions?
So if you look at the union of all the empty covering balls, then its union also displays some shape information. However, people mean a lot of different things by shape. So I wouldn't claim that our method can actually recover a very specific shape, for example, like a curve or something like that. However, it does give you a indication of what the zero zero density region look like.
But in your line example, the
Right.
line was sort of, you surrounded the line by an epsilon ball, um,
Hmm.
essentially where you expect to sample a few points. If you did sample a point in there, is it correct to say that you might get the homotopy type of the density zero region? You might say there's a hole in it, even though there's not.
So I think you might see a homotopy type if your zero density region is not too pathological. However,
Hmm.
if you actually your pathologic well, if your zero density region is a very small circle, and then you do not have enough samples, those covering balls may actually like instead of giving you a circle, it will give you a disk. So that will actually destroy your homotopy type. So to answer this question, I think it both depends on which homotopy type your zero density region have, and also like how many sample points you actually got to draw from your probability density function, because eventually our result is an asymptotic guarantee. In asymptotic, we all die. So
Okay.
yep.
Thanks.
Yep.
Okay, so any other questions for the speaker today? Let's see. Okay. So we do have a question in the chat window. Does your method work for RGB images as well, rather than grayscale images?
So yeah, I suppose the question is for our second part, right? Or
Yes.
okay. Sure. So one way is actually to do it for the RGB channels separately, because red, green, and blue channels can also be like put on 0-1 scales. And then the question, if we take that approach, one question me and my collaborator were quite confused about is how we actually join the results from different channels. Um, so for now, I would say no, but I think it won't be like too counterintuitive if we actually try to apply the combined methods into like RGB image, because the TOP method could be applied to the RGB image, while the active contour could also be applied to an RGB image. We choose the grayscale because it's relatively simple. Its response space is just a grayscale value. It's one dimensional. Um, so I hope that answer your questions. So the answer is no, but we're trying to work on it.
Yeah. Okay, great. Any other questions?
Yes, I have one question. Wojtek here. So my question is, will the result change if you, instead of using disks, you would use, let's say, rectangles with different ratio of sides?
So you're basically saying that we are trying to define our zero density region as a fractal. Am I right?
No, I want to, you are covering, in this example that Henry asked, you are covering things, with little balls. What instead
Right,
of
right.
balls, you are covering with rectangles, let's say, parallel to
Oh,
axis,
I see.
with
I
a
see.
different
So
ratio of sides. Will the results
right,
change?
right. So you're suggesting that instead of open covering balls, we use, for example, open covering triangles. Am I right?
Or rectangles when the
Or
ratio is 1 to
rectangles. Right. So for rectangles, since we can treat it as so our result works for not only for Euclidean distance, it also works for L1 distance. So in L1 distance, the covering balls are actually squares or triangles with equal size. In that case, our method works. But however, in that case, the order of smoothness should also be calculated with respect to the L1 distance instead of so here the order of smoothness is calculated with respect to a certain distance. So here we presume that the distance is L2. However, if you change it to L1, then the whole order of smoothness should be recalculated. Then that will also change your sufficient condition in our main results. We have a small section in our draft to discuss about that. Is that answering your question?
Yeah, thank you.
Yep.
Okay, further questions? Okay, so it sounds like there are no other questions, and in that case, I would ask you all to unmute yourself so that we can thank the speaker for